Hello everyone, welcome back. In this video, we'll be looking at sets and logic. So let's now begin with sets. So what is a set? Well, set is really simple. It's just basically just a collection. For example, let's look at this set A, which is just a collection of the numbers 1, 2, 3, -5. So this is just a set of 4 elements of these numbers. So now let's look at other examples of set. For example, the set of natural numbers, which is denoted by this fancy n. So the set of natural numbers is just all numbers 1, 2, 3, 4, and so on and so forth. Now let's look at the set of integers, which is denoted by this fancy z. So the set of integers is just -2, -1, like 0, 1, 2, 3, and so on and so forth. Now let's look at the set of rationals. So the set of rational numbers are any numbers which can be written in the form m over n. So any numbers which can basically be written as fractions. For example, 2 is a rational number because it can be written as a form of ratios, 2:1, as 8 equals 4, for example, 6 equals 3 equals 18 over 9. This just shows 2 is a rational number. So let's look at the irrational number. So quite obviously, irrational numbers are numbers which cannot be written in the form m over n. For example, √2 is not an irrational number, so is pi, so is the special number e. So all these are not the rational numbers because they cannot be written as the form of fractions, and we'll prove why √2 is not a rational later in the course. Now let's look at the real numbers, which are really important for us because we're doing real analysis, of course. So the set of real numbers is just basically all numbers, including the rationals and the irrationals. Now this is the notation for union of set, which we'll look next. So now let's look at set builder notation. So the first one we'll look at is union, which is just combining of two sets. For example, A is 1 and B is 2, 3. Then the A union B will be 1, 2, and 3. Well, the next one we'll look at is intersection, which is just looks for the common elements in both the sets. In our case, A intersection B will be the null set or the empty set because there are no two common elements which are both in A and B. The next symbol is this, which means member of. For example, in our case, 2 is a member of B. And the next one we look at is subset. For example, if we define A to be 1 and B to be 1, 2, 3, then A is a subset of B because the elements which are in 1 are also included in B. So A is a subset of B. So now let's look at from before. If you have noticed, the natural numbers, I'm sorry about that. The natural numbers are a subset of the integers because the natural numbers are 1, 2, 3, which are included in the integers, and the integers are a subset of the rational numbers because all the elements in the integers can be written in the form of fractions, and the rational numbers in turn are member of the real numbers. And we'll not be looking at this in this course, but the real numbers are also subset of the complex numbers, which you'll be doing in complex analysis. Now let's look at logic. Now we'll take a look at how we prove things and just working with mathematical logic. Sometimes the statements we look in this course seem intimidating, but it turns out a lot of the manipulations we end up doing are actually quite mechanical if you understand the rules underneath. So let's now look at logic and how we prove things. Writing proofs is a skill best learned by doing it over and over again and getting lots and lots of practice. A proof is an essay of some sort. It's just a series of steps that, when followed, should leave the reader absolutely convinced about the proposition you're proving. So when you're writing proofs, you should make sure that each step should follow the previous one logically. So let's now define a few terms. So statement. Mathematical statement is any sentence that is either true or false, e.g. 2 is greater than -2. That is true. Um, Root 2 is rational. This statement is false. So I hope you're getting the idea of what a statement really means. It's just any sentence that's either true or false. Now we'll look at some operators. First, we'll be taking a look at the AND operator. And the truth table for the AND operator is true, 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 false, false, true, false, false. So whenever it's true, true, then the overall statement will be true. So what does this basically mean? So let's work it out with an example. For example, root 2 is irrational and 2 is greater than -2. Now this first statement is true, so is the second statement. Therefore, the overall statement will be true, because when we look at the truth table, whenever the first statement is true and the second statement is true, the overall statement is true. Now, for example, if we change this to say root 2 is rational, then the first statement will be false, the second statement will be true, which makes the overall statement to be false. So now let's look at the OR operator. The truth table for the OR operator it's more or less looks like this. So for the OR operator, whenever either of the statement, it doesn't matter the first one or the second one, whenever one of the statement is true, the overall statement as a whole will be true. So let's look at an example. 2 is greater than -2, or 1 is less than 0. Now the first statement is true, but the second statement is false. But that doesn't matter, as long as one of the statement in the OR statement is true, the whole statement as a whole will be true. Now let's look at the if-then. The truth table for if-then is true, false, false, true, false, false. So true, false, true, true. Well, this is a weird one, but in a if-then statement, as long as the first statement is false, the overall statement as a whole will be true, as you see in this scenario. For example, let's look at the statement -1 is less than okay, let's look at this. 2 is less than 0. If 2 is less than 0, then 2 is greater than negative 2. Well, the first statement is obviously false and the second statement is true, but that doesn't matter. As long as the first statement is false in an if-then statement, the overall statement as a whole will be true. In this course, we'll be most like only looking at the first scenario where it's true, where where the first statement is always true and the second statement is always true. Next, we'll look at if and only if. So the truth table for if and only if. Bear with me here. True, 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 false, false, true, false, false. Remember, when I'm writing it this way, I'm just meaning the first statement is true, the second statement is these truths, these scenarios. So for if and only if statements, the overall statement is only true if both the statements are true or both the statements are false. So the overall statement will only be true in these two scenarios. Now let's look at some examples. Most of the theorems and proofs we'll be doing in this course will be if and only if and if then statements. So let's look at the strategy to proving these statements. For if then statements, it will be like P implies Q. If P then Q, we can also denote it using this one directional arrow. So the best way to prove such a statement will be to assume the first statement and then prove Q. So this is how we're mostly going to be doing it. There are different strategies for doing it. For example, if you're doing proof by contradiction, we assume P and we prove the negation of Q. For if and only if statement, it looks like this with a two directional arrow. So remember when we did the one directional arrow in the if then statement, we assume the first part and prove the second part. Since this if and only if statement, there are two steps we should follow. We should first prove this direction, and then prove this direction. So in the first step, we'll be assuming P and proving Q. In the second step, we'll be assuming Q and proving P. Mostly in if and only if statements, one of the steps will be really easy and the second step will be the more complicated one. Don't worry about these statements yet. We'll be looking at lots and lots of examples. By the end of this course, you guys will be experts at proving such statements and theorems. Hope you had a great time. See you next video.